A 2 kilogram bucket is attached to a massless string that is wrapped around a 1 kilogram, 4 centimeter diameter cylinder. The cylinder rotates on an axle through the center. The bucket is released from rest 1 meter above the floor. How long does it take to reach the floor? So this is a problem that involves a lot of concepts, and so let's try to move slowly and see what we need. The thing to identify, first of all, is what we want. We want the time. So I'll write that down. We want t. And as soon as you realize that you want time, you can think back to some of the first things you learned in physics, which were the relationships between time, position, velocity, and acceleration. So in terms of concepts, the concepts that we might want to think about are the so-called kinematic equation. Concept being kinematics, the mathematics of motion. The kinematics are the things that relate time to position and velocity and acceleration. Now I can already see that we've got two types of objects here. One, the bucket that can move up and down, and also the cylinder which can rotate. So let's also realize that we might need to use relationships between time and angle, angular velocity, and angular acceleration. So far, the kinds of equations that we might need, at least if we're interested in the bucket, let's make a list here, somewhat below. The kinematic equations for an object that has a constant acceleration, and given that the motion of the bucket is happening in the y direction, we could start to make that list, which looks like y equals y naught, plus the initial y velocity times time, plus 1/2 the acceleration in the y direction times the time squared. And you'll notice that we actually have most of the things in this equation already. We have our final y position on the ground, we have our initial y position, we have our initial y velocity, it's 0, and what we want is the time. What we don't have is the acceleration. In case you're wondering, don't we know the acceleration? Isn't it equal to minus 9.8 meters per second squared? The answer would be no. That's only the case when an object is undergoing free fall. Clearly the bucket is not undergoing free fall because it is connected via a string to some cylinder that's rotating. So at this point, we could use this equation if we knew the acceleration, but we don't. And so what that does is that reminds us that we probably need to reevaluate and come up with a new goal, which is to realize that we also want the acceleration in the y direction. That's where the next concept comes into play, which is dynamics. If you're trying to find an acceleration of an object and you don't have all the kinematic variables you need, chances are you're going to need to find it by using Newton's second law. So that in this dynamics, what I mean by that is using Newton's second law, which relates the net force to the acceleration. And so there we will need to remember that the net force on an object is equal to the mass of that object times the acceleration of that object. And that's all fine and well. However, because this falling object, the bucket, is connected to an object that rotates, the other dynamical equation we'll need is Newton's second law for angular motion, which looks like this. The net torque acting on an object is equal to the moment of inertia times the angular acceleration of that object. That assumes that the moment of inertia stays constant, which it certainly does for a cylinder that's made of solid material. So those are the equations that we need. And one more thing to point out is that we have a cylinder, and in terms of its radius and its mass, the moment of inertia for a cylinder is something that you can look up. It's given by 1/2 times the mass of the cylinder times r squared. That's assuming that it is rotating around its midpoint, which it is. Now, when we go to use the Newton's second law for the linear motion and the angular motion, before we can even do that, we're going to need a free body diagram for the two objects. So for the bucket, let's draw the object here as represented as a little dot. We have gravity acting on the bucket, given by its mass, little m, times g, and then there's a tension force being applied, and it points up. Now, I haven't drawn these arrows exactly correct. If the object is falling down, that means it's accelerating downward, and so in anticipation, I should draw the tension arrow as being a little bit smaller. In any case, this gives us the net force acting on this object, tension minus mg, equal to the mass of the bucket times the acceleration of the bucket in the y direction. Okay, we are again choosing to have our y direction be positive going upward, and so that would be an application of Newton's second law in the y direction. Several equations will emerge here. Let's call this equation 1. When we analyze the cylinder, we need to draw a so-called extended free body diagram. So here is what the cylinder looks like. There's its center. There are 3 forces acting on the cylinder. The force of gravity pulling down, its mass, big M, times g. There must be some support force keeping it upright. That I'll draw over here, and I'll call it F support. And finally, there's the tension force, which is acting at the edge, pointing down. And because the string is assumed to be massless, that tension force, T, really does have the same value as this tension force here. When we go to apply Newton's second law for rotational motion, we'll do that by applying it in this way. We'll determine the net force as being equal to the counterclockwise torques added together minus the clockwise torques added together, and that will be equal to the moment of inertia times the angular acceleration. Notice that I'm dropping here the vector on the torque and the angular acceleration because we are now working in the plane, and we can account for the direction of these things by either indicating clockwise or counterclockwise. Now, in terms of these 3 forces acting on the cylinder, only one of them applies a torque. You'll notice that the support force and the force of gravity both act at the center, and because the distance that the force is acting from the axis is 0, those torques are equal to 0. I'll remind you the general formula for that looks like this. The torque provided by any force is given by R times F times the sine of theta, theta being the angle between the radial vector and the force vector. What that means is there is only one force that is applying a torque, and it's making the wheel want to spin counterclockwise. And so that counterclockwise torque is given by the relevant distance, which is R, the relevant force, which is T, and the angle between the radial vector and the force vector is 90 degrees. So I can write in full RT 90 degrees. There's no clockwise torque, and so this is equal to 1/2 mr squared, putting in the moment of inertia, and the angular acceleration, alpha. And we can box that. That is our second equation. And now realizing what we're trying to do, we're trying to determine at this point the linear acceleration of the cylinder. It shows up here. We want that, but notice there's something that we don't know yet, the tension. Well, the tension appears in this formula, so we have a chance of determining it, but also there's an angular acceleration which appears. And so it seems that we have 3 unknowns, the tension, linear acceleration, and angular acceleration, and only 2 equations, which must mean there's a third equation to identify here. That third equation comes from relating the linear motion of the bucket as it falls down this way to the angular motion of the cylinder as it spins that way. That relationship looks like this. The linear acceleration of the bucket is proportional to the angular acceleration of the cylinder. It's kind of like asking, what is the acceleration of a speck of dust sitting on the edge of the cylinder? The proportionality constant is the radius of the cylinder. And now you have to get the signs right. The sign that should go here is minus, and that can be understood by realizing that the acceleration of the falling bucket is negative, but according to our conventions, the angular acceleration of the cylinder is positive. And so that minus sign accounts for that. At this point, we have essentially done all of the physics, and now what remains is to do the mathematics of solving for the acceleration and ultimately solving for the time. So these are the equations that we have, labeled 1, 2, 2, and 3. So the first thing I'll do is take equation 3 and solve it for the angular acceleration, and that would give us minus ay over r is the angular acceleration. What I'll do is I'll apply that to equation 2, and what that shows us is that the tension times r, sine of 90 degrees is just equal to 1. That's equal to 1/2 times m r squared, and the angular acceleration we just found, minus ay over r. Notice what happens is that, in fact, all of the powers of r cancel. Lose one from here and here, lose another from here and here, and what we determine is that the tension is given by minus 1/2 the mass of the cylinder times ay. So what you'll discover in this problem is that the answer to our question doesn't even depend on the size of the cylinder. Now that we have the tension, we can insert that into equation 1, which looks like minus 1/2 m ay minus little mg equal to little m ay, being very careful to distinguish big M from little m. With algebra, this can be rearranged and we can solve for the linear acceleration of the falling mass, minus mg divided by little m plus 1/2 big M. That will be the acceleration. Before we proceed, we should do a sanity check to see if this answer makes any sense. That sanity check, what we can do is play with, for example, the mass of the cylinder. As the mass of the cylinder goes to infinity, if that would become infinitely large, the denominator would become infinitely large, and therefore the acceleration of that bucket would go to 0. Hopefully that is consistent with your intuition. The mass of that cylinder being so big that essentially it would take an infinite amount of force to get the thing to spin. What happens as we let the mass of the cylinder go to 0, what you'll discover is you'll have minus mg over m, and so the acceleration of the bucket becomes minus g, which is the same as for free fall. Both of these conditions seem to be reasonable, and so we can proceed to finally get the answer we want for this problem. What we've just determined is the acceleration is given by that formula, and we have the kinematic equation that relates the initial y position to the final y position. So let's now apply these quantities here. When we determine the acceleration in the y direction, we have minus 2 kilograms divided by 2 kilograms plus 1/2 kilogram, all times 9.8 meters per second squared. What we get is a negative acceleration, 7.84 meters per second squared, and when we apply that to our kinematic equation, the final position being 0 on the ground, the initial position being 1 meter, the initial velocity in the y direction was 0, plus 1/2 the acceleration being minus 7.84 meters per second squared times t squared. That can be solved for the time, and you'll find that the time is 0.51 seconds for our final answer.